is warm now, so I know it was the yesterday was crazy. So hopefully you had rest, you stayed safe. So yeah, so the exam regarding the course, I think the exam one, the grades have been posted. In case you haven't seen, please take a look at your Canvas. I'm gonna send an announcement right after the class. So overall, the grades were good, right? But they were like some binomial, right? Some people were above 90, and several people they were under maybe 85 or 80. So for those of you that so the average was, I think, around like maybe between, I think it was 89 or 90, right? It's an average grade. So if you are lower than the average, so it seems that you underperform compared to the rest of the class. So I would suggest maybe attend the class, attend the office hours, utilize like all the resources that are available. Email me if you have any questions, just to make sure that you catch up with all the content. So this was the first exam. We're gonna have second and third exam. So if you didn't do well, so there are still chances to do better in the other exams. So we try to be very lenient in grading. So I'm gonna pass your papers to you on Friday, but generally we didn't try just to penalize if you did like some small calculation or some mistakes. So this is about the grades. So is there any questions, concern about the grades? We can discuss it now. But anyways, I'll return your papers on Friday. If there is any issue, feel free just to let me know. So regarding the course, so next week is a spring break. So we have this Friday class, but generally just make sure you start working on your project two. Project two is basically our first major project. We're gonna have project three and project four, which are built on this specific project two. So project two has two problems. One is a maze problem, which you have to at first implement, then to be able to apply dynamic programming over that. And it has one biological problem. Still, you have to implement it, learn the transition matrix, implement the transition matrix to be able to learn the policy. So we will use the same sets of problems for other projects. So just make sure that you do a good job in project two because it's a base for other two projects. And this project is not like a previous project. Please make sure to provide as comprehensive as possible the interpretation of your finding. If we ask, for example, to show the effect of transition probability, if it is low or small, explain exactly what happened and what the result reflects in your experiment when the transition probability increases and why it is. So some people just say that, look, these are two results, lower, higher. So we cannot give a grade if there is no interpretation, right? I'll ask TA to send another announcement, but once you put your result, your code, please explain them and provide your justification. If your justification is wrong, at least we have some basis saying that, okay, at least you try to provide justification. But if there is no explanations, then we cannot provide the grades, right? So just note that. Then we're gonna post homework three next, I think on Friday. So it will be your next homework in a sequence of our homeworks. So regarding the 2 days lecture, so this is exactly a place that after exam one, we move from dynamic programming and optimal solution to real reinforcement learning, which is interactive solution. The difference between them is that dynamic programming provides the optimal solution when you know transition probability, when you define reward, and you write all those Bellman equations to be able to solve it. On the other hand, that's not always possible. When we call it interactive learning, meaning that like you interact with something, you get the next state. You may not know the exact state transition. For example, in a stock market, if you make, let's say that an investment today, do you know what's gonna be your next state? Meaning that how much wealthy you're gonna be in the next time step? We don't know. And there's no equation to drive that. But can we learn as we interact? So that's something that reinforcement learning is excel at. And we're gonna connect all the dynamic programming concepts to reinforcement learning in the next part of the course. So today is a bridge, but from the next lecture, we're gonna start with the SARSA, Q learning, all those dynamic programming content. So today we're gonna connect at first the regular dynamic programming with approximate dynamic programming, which these topics were the center of attentions for years. Like we talk about the asynchronous dynamic programming, generalized policy iteration. Then we go to Monte Carlo techniques, which connects dynamic programming to temporal difference learning, which is temporal difference learning is reinforcement learning. I'm gonna talk about that. So let's start with a quick review. So just we are not gonna again talk about the dynamic programming. Just I'm gonna provide the formulation of matrix form for value iteration and policy iteration. The reason that I put matrix form because they're easier. Look, vk plus 1 value iteration says that it max over a in a. So r s a plus gamma transition probability vk of vk. So this is value iteration. So we know that the max applies row wise. This is transition matrix, and we start from v0, then we get v1 after applying this row wise. Then until vt and vt plus 1 they don't change, then they are v star. So once you have v star, pi star is equal to arc max of row wise again, r of SA plus gamma P of A V star. So this is just one time at the end. So the reason is that, look, if you look at this equation, if you put V0, you get V1, V1, V2, V3, V4. Until this V doesn't change. If V doesn't change, this equation becomes V star, V star. Why it becomes V star? Because this is exactly Bellman optimality equation if both sides are V star. Bellman optimality equation says that for optimal policy, the V star is exactly maximum of all the here V star, Bellman equation. That's true just for optimal policy. So this becomes V star, and if you have V star, this becomes your optimal policy. So this is about value iteration. For policy iteration, so we had two steps: policy evaluation, policy improvement. So in matrix form, your policy evaluation, it becomes Bellman equation. Bellman equation says that V pi is equal to, right, R of S and pi of S, then plus gamma P of A V pi. So this is a Bellman equation. So had this Bellman equation, if you want to solve it, bring the left, right, everything, so it will have a closed form solution. V of pi is always I minus gamma P of A inverse V pi. That's it. So sorry, this is R of not V pi, R of S of pi. So this is a exact solution. So we know that we can have approximate policy evaluation too. At approximate policy evaluation, it says that V of k plus 1 is equal to R of S of pi plus gamma P of A is exactly Bellman equation, but you write it in this way. So you iterate from V0, you get V1, but you just follow policy pi. Then until Vk, let's say Vt and Vt plus 1, they don't change, then Vt plus 1 is equal to V of pi It's not V star. Because we apply Bellman equation, not Bellman optimality. So in either case, you could get V of pi. Once you have V of pi, it's policy improvement. Policy improvement says that pi prime, that is better than pi, is arg max of, so R of SA, there is no pi, right? Because there is a max here. Plus gamma P of A to V of pi. Look, this is a policy improvement, meaning that if this one was V star, this would be pi star. There is nothing better than pi star. So this becomes a special case of the previous one. So these are the matrix form. Matrix form, you see, it's much easier to digest and much easier to understand, right? So you can always refer to this when you wanna really understand the problem. So both, they give you the same result, either vector form that we had before or matrix form. Just the point is that this transition matrix, its size P of A is n by n. An n by n matrix, if the number of states are large, could be extremely large. For example, let's say that you have a maze problem, like the one that we solved. Let's say that it is 10 million by 10 million. So can you solve it? Like 10 million by 10 million, this becomes too large. So what's the problem of becoming large? Even keeping it as a memory is large. Inverse of it is large. Everything is large. So, but what if these are like very sparse? Let's say, for example, from this state, you can go just to 3 states. Means that out of 10 million, just 3 or 4 are non-zero in each row. Then it doesn't make sense to keep this matrix. You use vector form. So when we have a sparse transition matrix, vector form is better. When we have kind of like a transition matrix that is full, we call it like a full rank, then we could use the matrix form. And when this n is a small, by the way, right? So that's about the dynamic programming. We finish the topics here, but just I want to stop here in case you have any questions.
Could you just repeat one more time when you would use vector versus matrix form?
Sure. Yeah, so you know the vector form, the difference is this. The vector form, it always has like this vk plus 1 is equal to either max it has or it doesn't have summation of s prime. P of s prime given s and a. So, but here, if you are at one specific state, you take one action, the next state is one row of your transition matrix. It's like your S prime 1, S prime 2 to S prime n. So the point is that if, let's say that, for example, in maze problem, if you are here, you take one action, you could go here, here, here. Means that at most 3 elements of these gonna be non-zero. The rest are always zero. So this is a sparse transition matrix, meaning that these values, like these summations, is over just like 3 numbers. 3 out of what? 3 out of like 10 million. And the reason is just the rest are zero. It doesn't mean they don't have transition, their probabilities are zero. So in these cases that when you look at your transition matrix, you see a lot of zeros, which is happening mostly in robotics. When you are in one state, you take action, your next state is limited. You cannot like take action suddenly from here, go to moon. So in those cases, we always use vector form for a sparse transition matrix. The reason is two things. It's just like memory we save. Because why do you want to save all those zeros? And also computationally inverse of matrix. So, but if the like non-sparse transition matrix, always use matrix form. It's much easier. Does it answer your questions?
Yes, thank you.
Of course, yeah. So, any other questions about dynamic programming? Okay, so now let's move on to approximate dynamic programming. Again, I mentioned these topics were really popular in between 2000 to 2013, 14. So we're gonna pass it very fast, but all these ideas, all these attempts people have done in approximate dynamic programming are directly used in between 2020 to 2025 or 6 for advancing regular deep reinforcement learning. So you're gonna see here, and then we're gonna repeat it in later on in DeepRL. So, like the idea of approximate dynamic programming starts that what if my states are too large? Let's say, for example, I have S1, S2 to S1 million. So I cannot either solve it through matrix form or through vector form because it still is costly, even vector form. Let's say again, you have a maze. Let's say that you have 1 million by 1 million. There are a lot of problems that the state space could be extremely large. So if you use matrix, clearly is not possible. This is too large. And if you use vector, it's still too costly. Costly means that, like, imagine you have summation over S prime, P of S prime given S and A. It's 1 million of this. Unless it is S sparse, but if it's not S sparse, right? So it's extremely large. It is like S by, so the transition matrix is S by S. So value iteration we know is like this. Vk plus 1 is equal to, let's write vector form, is maximum of A in A, summation of S prime, P of S prime given S and A, the reward plus gamma V of K of S prime. This is a value iteration backup. So if I start from V0, let's say that everything is 0. What is the size of this V? It's 1 million. Then I have to apply value iteration backup to go V1. So how many of these value iteration backup I need to apply? 1 million. Like for each state, you want to update this, you have to update according to this. It's costly. Then you want to calculate V2 and you want to go thousands of iteration of this. What if this 1 million is 10 million? Right? So generally, there is a in-place dynamic programming proposed that it just saves for us a space. Like if different dynamic programmings have different roles, this specific one is just for memory and a space. It says that if you think about it, this is your V of old, right? If like your V of current point, then you use this to find V of new. That's how it works, right? So now it says that if you have V of old and you want to get V of new. So what if you just say that, like if you think about it now here, I update this according to what? Look at here this equation. I update Vk plus 1 of S1 according to Vk of all the previous state. Means that I leverage all these Vks at all the states to be able to update this. Then I move to the second one. I use the Vk at all the previous state to update this. So it says that what if you don't do that? You just do it in a single V. Let's say that I have one single V. It's in this way. Single vector. So let's say, for example, you want to update this. You update this according to everything here. Then you update this according to everything here. So they call it in place. You don't have like one old, one new, then new should be filled out, then becomes old. As you update each of them, you just replace them, right? So it's as simple as things. The only saving here I had to always keep two vectors, always. Either it's old or new, right? So both of them I had to keep to be able to update. Here, I have just one single vector. So v, like when I want to write vk plus 1, right? So you can write like v of s is equal to maximum of a in a summation of s prime p of s prime given s and a reward plus gamma v of s prime. So that's it. So is it, so how much saving we have in memory? So we just do, it's not is a state length, right? So instead of having two number of states, two vector, I have just one vector. Does it converge? Because like Bellman equation doesn't say that this has a fixed point solution or Bellman optimality. No, it doesn't. There is no proof of convergence for any of these approximate dynamic programming. But people have used it. Empirically, it works, but there is no guarantee that it will converge. So one person may say that, like, one question I have, do you think that would it matter if I use one single vector? Like if I had two vector, I could update this at first according to this, then I would go this according to this. But do you think that if I have one vector, does it matter I start from top to bottom or bottom to top? Let's think about it. Like, for example, if I update the first element here, right? So I update according to the rest. Let's say everything is 0. I update this. Then this becomes non-zero. Then when I want to update the second one, I update the second one according to latest thing. So it would matter if you would start from bottom to top or top to bottom, it would be different. So that's something that it doesn't really converge, right? There's no guarantee of convergence, but it's just saving the space. It's called space efficient dynamic programming. So the second modification is prioritized sweeping. This is likely the most popular one that is widely used in deep reinforcement learning. So look, the idea is interesting. It says that, do I need to backup means that apply value iteration backup for all the states or no? So if you look at the value iteration, we have this. It is maximum of summation of s prime p of s prime given s and a r plus gamma of v of k of s prime. So if you remember in the past, we had a maze problem, right? So in the maze problem we applied value iteration backup. The only place that changed too much was near the goal. The others, they didn't change that much. So if you start, for example, from V0, let's say everything is 0. If I apply value iteration backup, means that I apply these for all the states. So I'm going to get V1 to VT in this way until it converges, right? VT plus 1. So the idea is that if you find the maximum difference between them in 2 iterations. So let's say that, for example, here in one step, this becomes 99, the rest stays 0. In the next step, few of others changes. So you can see some of these values at some states, they have larger change. So for example, if you want to find the maximum difference between V0 and V1, so basically it's a maximum over a state. So some elements gonna have the more changes, right? Maximum differences. Let's say, for example, you have again all 0 this. So this is just for this state is 99. This becomes 99 maximum, but it's associated to this state. So do you agree that if I want, like, let's say that, for example, I reach to here V99, V100, V101. Let's say that all the elements are the same, just one element is changing. Do I need to apply this value iteration backup for all of them? Because when they don't change too much, what does it mean? It means that either you apply it or you don't apply it at this stage. These are almost constant. They don't have that much potential to change. For example, those states that are near the goal, we're gonna see in the example. So quickly, they're kind of 99 or their goal positivity gets distributed across different states. So should I do more backup on those states that making sure those goal positivity reaches to the states that are very far? So that's the entire goal. I don't need to apply heuristically, not in a guarantee way. If some states they become constant, there is no change between them, and some of them every time I apply value iteration backup they are changing, I can just apply value iteration backup according to the changes, right? Because the changes are the ones that leads us to a stopping criteria. If that is specific value, if all of them are the same, that is specific value is still changing. So let me just make sure that that would converge quickly, then the rest hopefully would stay the same. So yeah, so what should we do? So there is a priority very popular in deep RL. It's called priority. Priority means that I want to prioritize for those, just apply value iteration for those that there is a huge change in their values as I move. Means that either they are closer to goal or the goal positivity is getting propagated. So priority is a vector of size of a state. So each element specifies priority of a state, for example, S1. This is for a state S1. So delta of S1. This is delta of Sn, if I have n state. So this priority, if they are higher, means that they are high priority, means that their changes are too much. So I can like normalize it. So this is P of priority is like delta, let's say priority for state I is delta I over summation of delta L. It's just normalizing this gives us a probability as far as these deltas are positive. So then, so the priority basically is a vector, is a normalization of the vector of this. So I call it P is a normalization of delta. So at the beginning, if everything is 0, no change has happened. So priority is 1 over n. If I have n states, means that I don't know, there's no really a state that has more potential. Then the way that it works, instead of like value iteration, you update for all the states, you pick one single state according to this priority. So now that single state that you want to apply value iteration backup is random across all the states. So you could start from the middle, you could start near the goal, anywhere. So let's say you pick this state. So look, this is the size of a state. So this means one index from this probability. So once you do it, you apply regular value iteration, right? You say that, okay, V of NEU at state sk is equal to maximum of summation of S prime, P of S prime given S and A, R plus gamma V of old of S prime. So I just apply it for sk. It means that like if I have a vector in this way, so I pick a sk here, this is sk, I apply its V here. So now you change the priority for the state k. So priority for state k is delta of sk that is selected. So how much was its old V? And how much is new V after update? So it's like V of new at state sk. Did it change compared to old of sk? Absolute value. If it doesn't change, means that it's not really near the goal. Means that really picking it didn't give us a step closer to convergence. It's already zero. It was zero, right? So then you find its delta. Then this is a key point here. Once you do this, you have to do for all the states that end up at sk. So you have to update also delta for all the states that there is a connection between them and sk. Means that like you could come from those states to sk. Means that you go one step backward. Means that what are those? Let's say that what are those? Let's put gamma max a in a. So what are those states that potentially I could come to sk from them with any action? I don't care what is the policy. It's like you go one step backward. Then you say that, okay, this delta sk should be propagated to them. So this delta of sk goes to the states that could potentially lead to sk, all of them. Then you add with their previous delta, and there is one gamma. We're gonna see why it works. Let's see through the example. So let's start with this maze problem that we had. So let's start with first delta. What is the initial delta? Delta cannot be zero because normalization of zero becomes none, right? Not defined. So let's say delta at the beginning is a priority for all of them. It's one. So why it's one? Because I start from V of all everything zero, right? And let's assume this is a deterministic environment. So if delta is one, means that everything has initial priority the same. So what would be my P priority would be 1 over how many states I have? This is the size of 15 states. 1 over 15, 1 over 15, 1 over 15. The normalization of delta gives us P probability. So now I have to pick one SK from this P priority. Let's say I pick it, and let's say that your SK becomes by chance, right? Randomly, it becomes 14. It could be any of those 15 states. So if it comes 14, so V of, so initial V is 0, just initial V is 0 for everything. So V of 1 of, or I call it V of NEU of. NEU means V of 1 of. State 14, SK is, just write Bellman equation, right? Maximum of A in A, summation of S prime, P of S prime given S and A, reward plus gamma V of K of S prime. So if you start, is a deterministic environment, right? If you start from a state, this is a state 14. If you take action, let's write max. So let's write for action up. So if I take action up from 14, so what is the next state? It's 11. Its probability is 1. How much reward I get? -1 from 14 going to 11. Plus gamma, let's say is 1 for now. It's never 1, but just for simplicity of our computation. Gamma V of next state, V of old of means that V 0 of state 11. That is 0 at the beginning. So this becomes for now -1. So what about for down? It is 199 plus gamma V of goal. V of goal is 0. So this becomes 99. What about for left? For left becomes 1, -11 plus gamma V of old of 11. That is -11. And right, so right becomes 1, -1 plus gamma V of old of 13, which becomes -1. So the maximum of this becomes 99. This is something that we knew from the previous topics, right? So it's a value iteration backup. So 99, what was the previous number? Was 0. So how much your priority should change? Means that how much you gain after applying this value iteration backup, how much it change your V, how much potential it has, right? So V of 14 is just the difference between V of new at state 14 minus V of old at state 14. If it doesn't change, it means that next time don't do it. It's 0. But if it changes, then this becomes, what is it? The difference? The difference is 99. Because it's 0, this was 0, this got 99. So you can see it's a huge potential, right? So then this is for selected state, SK. But it's not the only state that we updated. We also update for any state that could end up to state 14. Like, look, what are the states that previously, not in future, I was there, I could come to 14. So 11, it was possible. 13 is possible. That's it. 14 is possible too. Is that correct? Because from 14 potentially could be my previous state. So it says that you update the delta for all other states except 14. Except basically SK that lead to SK. So delta, so what are the states? So the states here are 11. Look here, if you look at 14, previously I could be this would SK minus 1 could be here. The other one is 13. I don't put 14 because it's not counted. I already updated 14. So I update delta of 11 according to this equation. Is a delta of 11 plus gamma maximum of this P of. Look, this is SK, which is 14. This is the states that you would be, like P4. It is 11 and one action plus delta of is 11. The same we could have for 13, which is delta of 13 plus gamma max of A in A, P of SK, which is 14, given S is 13, and A, delta of 13. So what is the original delta for 11? Look, original delta for everything is 1. So this is 1. So what is this? So this is, so here I put wrongly, look, this is propagation of uncertainty at state 14, SK. In this way, right? So this delta is 99. This 99 gonna be propagated to states that we could end up to SK. This is 99. So what are the actions? Here is a deterministic environment that I would take from 11 to come 14. So down, look, with probability 1. So this is 1, and this is for down. This is 1. So this becomes 1 plus 99, 100. The other one the same, 100. So now after just one update, I have a new delta. That the delta for state 1 is 1, state 2 is 1, state 3, state 11, right? So 11 state here is 100, 12 is 1, 13 is 100, 14 is 99, 15 is 1. Is that correct? So priority after 1 has changed. Now that I have priority, my next state is coming from this priority. So let's say, for example, you get your, so you have to normalize this in case I didn't explain in a good way, right? This P is 1 over the first element, 1 over summation of all the delta L. So the other one is 1 over this summation of all delta L. So this is 100 over this. So if you update this, you're gonna see the priority for these elements are larger, the others are very small. Again, it's sum to 1. This is a priority because we normalize. So if you again generate P, we know that here the chance gonna be more on state 11, state 13, and state 14. Let's say by chance again, state 14 is selected. So now let's find the V of NEU of 14. V of NEU of 14 is the sum maximum of, it's value iteration backup, right? Maximum of A in A, summation of S prime, P of S prime given S and A, reward plus gamma V of all the S prime. Okay, so what would be for up, down, right, and left? So for up, if you are at state 14, if you take up, so you go with probability 1, you get -1, and you go to state 11. State 11 is gamma V of 11, V of all of 11 is 0. So this becomes -1. For down, it becomes 99. For right, it becomes -1. For left is like it becomes 1, -11 plus gamma V of all of 14. V of is 99. So this becomes 88. So the max again is 99. That is for down, right? So delta of 14, the way that for the current state, right? This is a current. For current state, delta of 14 is always absolute difference between V of 14 old and new. Absolute value, right? So it doesn't matter how you write it. So the previous one was 99, now it's 99, it's 0. There is no other priority for this. So had this propagates to other, so what would be delta of, so let me write other states ending at 14. So we know that one of them is 11. It becomes delta of 11 plus gamma maximum of action P of 4. Look, it's always here. It's going to be 14 given 11 and action delta of 14. Delta of 14 got 0. This doesn't matter. It's 1. Then this becomes delta. So this stays 100. It doesn't change. The same for 13. It stays 100. So now I have one new delta as a vector. That is 1, 1, 1. For state 11, it is 100. 12 is 1. State 13 is 100. State 14 is 0. State 15 is 1. So you can see the priority after one step got, now one of these two will be selected. Then it will propagate from these 13 and these to 12, 10. So you prioritize much faster, you propagate the deltas. So is there any questions here? I'm not going to go more deep on the steps of this, but this is a very efficient algorithm, especially for problems that are river has like one center. Let's say, for example, you have a goal. You have a cliff that has a very negative value. This quickly propagates it, right? Compared to just doing everything at all iterations. So any questions here? Okay, so look, there is a book, very popular book, is called Approximate Dynamic Programming. It is by Warren Powell. He's a very popular, he's a faculty at, I think he got retired from Princeton. So he has done a bunch of textbook in approximate dynamic programming. So this book is excellent, right? In case you are interested, but it connects it, the latest version is online available. So you can download the PDF. It connects it to several topics in deep RL2. So one other variation is called real-time dynamic programming, all heuristics, right? Just it says that V, K of, let's say that you are at one state SK. Let's say you put your robot in one environment. You are at one specific state. Let's say, for example, I am currently at this state. Real time, meaning that you update your value as if you are learning in this environment. It's not like offline, you have value, you update. So you are at this, your robot is in this location. You update V of this exactly like a value iteration. Summation of S prime, P of S prime given S and A, R plus gamma. So when I call R is R of S, K, A, and S prime, plus gamma V of K of V of S prime. So this is the way that we update it, right? So we update this at state SK, then according to max. So let's say I updated, let's say everything is 0 at the beginning. I update for this. What would be if I update for this according to this equation? Let's say everything is 0 is a deterministic environment. This is going to get -1. So now that is -1, I have to, because it's a real-time dynamic programming, I have to take action too. Action doesn't have anything to do with this. I have to take action to move to the next state, either left, right, down, it doesn't matter. Then update this. Then move here, update this. Then move here, update this. Move here, update this. Just as I move in the real world, I update. So how I move, we never talked about this. It's like getting closer to reinforcement learning. How can I move then after updating for one? So this update is gonna be arg max A in A, right? So summation of S prime P of S prime given SK and A, R of SK, A, and S prime plus gamma of V of S prime. So it is not like really optimal solution, but it says that just exactly after updating this, go argmax. So for example, here, you updated this, got -1, right? So what would be the maximum value? Either right would have the same value and left. Down would have -11. Up would have now -2. So it says that either go right or go left. Right? Then from that place, you update for that point, take another action. Right? So this is called real-time dynamic programming. So any questions here? I'm not gonna solve anything. It's just like the idea.
Professor, can you explain how that is, I guess, real time? I still don't kind of understand why it is.
I see. So real time means that it's like not like a planning process. Let's say that you put your robot in one specific state. Like it's a real physical robot, right? So now at this point, every value is 0 at the beginning. You have a vector of V0 for all the states. Then you picked one state. This is your current state. This is state 7. So at this state, you apply this value iteration backup. If you apply value iteration backup, it has maximum of everything, right? So if you go take up, then the value gonna be 0. You're gonna get -1. If you take left, you're gonna say -1, -1, and -1. So the maximum here, this V, gonna be generally -1 after applying value iteration backup. Now it says, okay, your robot was here. What should be the next? Because I want to move. I don't want to update for all the states. I want from here to move somewhere. Either stay, go up, go down. So take one action, whatever that action is. Let's say I go up. Then I update for this the same way.
Okay.
Then I take another action. Maybe I come back down again. That's okay. I update for this point. As I move in this environment, just I update the value at those states that I observe. It's in real time, right? Like as you move, you experience that point, you update your value, right? So this is instead of updating for all those tables one by one, then going to move on, just you update for your current state.
Okay.
You can just think about putting a physical robot moving around in this maze. Wherever it is, you just update for that specific one.
Okay. Got it. Okay. Thank you so much.
Yeah, of course.
Professor?
Yeah.
Yes.
Okay. I would just I just wanted to know if there's some sort of bias for picking like the first state that we want to apply this on. Because it looks to me like if we picked 14 as the first state, it's going to be faster than like if we picked, say, a state like 5 or 6.
Right.
So is there some sort of bias in like picking the first? Do we pick states that are closer to the goal like first so that it's easier, or what?
So that's a great point, right? So if we know where is the goal, right, we could always put priority. Let's say, for example, there is one goal here and there is one other goal here. So we could exactly put priority according to their distance from the goal. It's called distance to goal or cost to go, right? Just that priority that we had in previous one, like delta, you could manually set. But in real world problem, you don't know where is the goal, right? If you know the goal, you can always start from goal and come back. If you don't know the goal, then you have to start randomly, right? Does it make sense?
Oh, okay, got it. Thank you.
Of course.
Professor, so
Yes.
the real-time GPU is actually developed to applying in real-world empirical environment. So I just have some problem about if the algorithm was applied in real world, then what about the transition probability? Do we assume we know that, or we actually run an expectation version of that?
So we assume we know it, right? So, but if we don't know it, we cannot apply this real-time dynamic programming. We have to apply like Q-learning, SARSA, right? Some of the others. So these are like, again, approximate dynamic programming, still assuming that we know the transition probability. Is our next exactly topic, right?
Okay, yeah, thank you.
Any other questions? Okay, so the last thing I want to say in this topic is the generalized. This is a topic that is still you see a lot of paper, right?
Oh,
So
sorry.
generalized, yeah.
Oh, sorry. Yeah, so, but I mean, even if we assume we know the transition probability, the reward here should be unknown to us, right? We only know what's the reward we actually get for the action we choose.
That's a good point. So you say that even if we know the transition probability, if I want to pick the next action, right,
Yeah.
I need to have R of S and A without S prime. But if
Yeah.
you know this and you know this, you can get this, right?
Yeah.
So here it assumes that basically both transition probability and the rewards are known.
So even if the reward is not actually the new state we go into. I mean, for example, there's a 2 probability that we may go to
Right.
state 1 or state 2. We only go
Right.
state 1, but we know both the reward.
But we are using the expected value of S prime, right? Look, this expected value, for example, let's say, for example, you are at 13.
Yeah.
If you take left on expectation, you could go to 15, you could go to 12, you could go to 14, right? On expectation, you get negative 11 with 0.9, but with 0.1 over 2, you may get negative 1. With 0.1 over 2, you may get negative 1. This is the expected value of action left, right? So this is basically if you multiply this with this, it just gives you go to the direction that on expectation with respect to next state give us the highest expected reward and also the value.
Oh, okay. Yeah, I see. So the reward itself is also an expectation
That's
version.
correct. Yes, exactly. S prime has been, because we haven't seen S prime, we are marginalizing out.
I see. Yeah, thank you.
Of course. So this generalized policy iteration, it's basically every family of policy iteration or value iteration can be written as a generalized form, which is generalized policy iteration. So I think I talked about it in the last lecture, the last part, but let's just review it. Let's say if I have policy iteration. Policy iteration starts from pi 0. It applies policy evaluation. Policy evaluation is what is it? It's Bellman equation. Then we get V of pi 0. Then we apply policy improvement. Then we get pi 1. Then we apply policy evaluation. We get V of pi 1. We stop until the time that pi doesn't change in 2 consecutive steps. So if you take a look at it from the approximate policy evaluation. So when we have pi 0, we start with 1 V0. What is V0? Is all 0. Then in approximate policy evaluation, I apply this one, I get V1. This is under policy pi 0. Right? So basically, if you want to see what is approximate policy evaluation, it is Vk plus 1 of S is equal to summation of S prime. There is no max. S and pi of S R plus gamma V of K of S prime. So this is everything is under policy pi. So you get V1, then you apply, you get V2, until you reach to 1 Vt, then you reach to Vt plus 1. If these Vt and Vt plus 1, they don't change over time. So this V has applied to V pi, has converged to V pi, 0. Then you apply policy improvement. Then here you start, you go to pi 1, then you apply, again you start from V0, you apply V1 until you apply to Vt in this way. So basically you can think of it as applying this equation over and over in this way until this V doesn't change, then is V pi 0, then improve it. So the idea is that, can I, instead of going, look, this could be many steps until this converges. Can I cut it here? Let's say I go 1, 2, 3, it still hasn't converged. Then improve it, then go 1, 2, 3, then improve it, then 1, 2, 3, then improve it, 1, 2, 3, improve it. Right? I don't want to go till the end, then improve it. It's just too much. It's approximate, right? Because we know according to equation, I should have V pi 0 to improve V pi 1. We know that. But is there a possibility in an approximate way to stop here, then improve it, then stop here, improve it? That's a question, right? So just to say that it makes sense is this. So let's say, what is value iteration? Value iteration says that Vk plus 1 of S is equal to maximum of A, summation of S prime, P of S prime given S and A, R plus gamma V K of S prime. So look, if you look at this V0, let's think that V0 is this at the beginning. This applies, like, look, if you look at this part is over 4 actions, like different actions, A1, A2, A3, for example, A4. Then you pick the max. So here on top here. So I apply this under a fixed policy. I don't apply it over different actions. This is always pi 0. Look, for example, this is pi 0 until I converge. Then when I converge, I want to see what is this specific step here, this line. Look, this is policy improvement. Policy improvement says that your pi 1, that is the improved policy, is arg max of summation of S prime, P of S prime given S and A, R plus gamma V pi 0. So you basically use the last V here to get pi prime, pi 1. So, and look at this equation, it's arg max over summation of this. So when you have V0, you have this. So I want to you connect this one, policy improvement, to this value iteration. Look, the difference between this and this, assume that this is arc here, right? The only difference between the right side of these two is that this is Vk of S prime here. Here I have V pi 0 of S prime. Like this is your previous policy, you improve it, becomes pi 1. This is still your V0 or V1. You apply it. So the point is that if you think about it, right, this specific element for 4 actions give you different policies, right? Like for action 1, action 2, action 3, action 4. So you calculate it. It's like calculating this for A1 is like in your mind. This is like policy evaluation, approximate policy evaluation step. Because look, you give this one, if the policy was A1, this update here for me, if I would put it here, would be exactly under that policy that is A1 at the state S. This would be under policy pi 2, this. So this is basically approximate policy evaluation for 4 actions. But I could really do it, but I quickly improve it. So you can think of it, value iteration is basically one step. Policy evaluation plus policy improvement. Look, as soon as you try to evaluate it, here is evaluation, right? Because from V0, you apply under a given policy, you find a V. This is basically your V1. Under action 1, under action 2, under action 3, under action 4. But quickly, immediately you improve it. So basically, if you think about these steps here we have for policy iteration, you have pi 0. Let's say you have V0, all are 0. Instead of applying finding V1, automatically you apply evaluation plus improvement, you find V1. That would be value iteration backup. Evaluation policy improvement, evaluation policy improvement, and you move on until you convert. So it's up to you. You want to follow a policy, then improve it, or you want to do policy evaluation and improvement both at the same time. So that makes both of them in the same category. It's called generalized policy iteration. So we already know this process, if I cut these to one step, it becomes value iteration. If I go all the steps, it becomes policy iteration. But is there anything in between? Let's say I go a few steps, then I improve it, then I go a few steps, I improve it. Before converging under current policy, I go, I improve it. I go, I improve it. That becomes generalized policy iteration, right? So any questions here? Okay, so let's move on to our next topic, which is Monte Carlo methods. Look, it's a first part that we finished the approximate dynamic programming, we are going to RL. But interestingly, the motivation comes from the fact that what if I don't know the transition matrix? What if I don't know the reward? But there is a very important here, but that we have one simulator that if you give S and you give A, it gives me S prime. So what is this simulator? Let's say you have a robotic simulator, very complex visual. Your robot, let's say autonomous car, like let's say the game that you play. This frame is your current state. It's your frame. You take one action, you are a game player. You take one action, then the next state comes. So the next state means next frame, for example. It's stochastic. We don't know what is it. But after taking action, we see it, right? So I don't know exactly what was its probability. Was it like always would come this frame, or every time it could come other frame? So I don't know those, but I know if I am at state S, I take action, I can just get one realization of next state. So means that most likely there is one pi of S prime given S and A that we don't know. It's a simulator. But my next state would come from this. Like your SK plus 1 comes from this SK and AK. It's just one sample from this. Let's say, for example, you have a very complex wireless network. The state is the status of this wireless network. You take one action, you change the bandwidth, you do something, then your complex simulator gives you the next state. You get just one sample. You don't know how much is probable, but it's one definitely probable that I see it, right? This is called Monte Carlo. It means that it's a sample-based approach. So I don't know the transition probability, but I can get a sample from this transition probability. I don't know the exact, I know the reward, right? But if I see S prime, I know that, oh, from SA, I went to S prime, so it's out of SA and S prime. So it's better not to say, I don't know the reward. I know the reward, but I don't know the transition probability. It's more accurate. So, like, what's the problem? So let's say about the general dynamic programming, value iteration, policy iteration, whatever, right? So they rely on always equation like this. It is max summation of S prime, P of S prime given S and A, R plus gamma of V of K of S prime. So do you think that, do I have this? No, I don't have this. What about this reward? Can I have this reward or not? I know the definition of reward, right? But I haven't seen S prime. So if I am at state S, I take A. I don't know what are the probability of next state. So I don't know the reward. Because if I want to know the reward, R of S, A, S prime, I need next state. One of you may say that, oh, so use R of S and A, not S prime. So if I want to calculate this, I need transition probability. R of S, A, and S prime. Look, I don't have this. Because of this, I said I don't have reward, right? So in reality, it's like this. You have a state, you take action, you observe the next state, and you may observe one reward. That's how RL works, right? So you really don't know. How do you calculate this reward? So if you know the current state, you take action, you get one next state, then you know this is R of S, A, and S prime. You know this. The definition is known, but unless you observe, unless if you don't observe S prime, you cannot calculate this reward. So then we go to basically a Markov decision process that I had a state space, action space. Do you remember I had transition probability, reward, and this? Still I have definition of reward, but I cannot use it because I don't have S prime. these two. So let's come back to the original problem. If I have a Markov decision process, instead of these two, I have a simulator. When I say simulator, just notice there is a S prime and R that comes from this probability of S and A. If I have S and A, if I apply them, I could just see a couple of one next state and reward. That's it. So can I apply dynamic programming? No way. Can I apply Bellman equation? No way. Everything needs transition probability and reward. Can I apply policy iteration? No. So there is nothing I could apply if I don't have the model. So what can I do? So if I have the policy, so what is pi star? Pi star, we cannot write Bellman equation. Let's come back to the original definition. It says that over all the policies that I have, I can get V of pi. So basically it means that if you have pi 1, calculate V of pi 1. We are coming back to the original problem. S to the power of A, calculate V of S to the power of A. If you calculate this, then you have pi star as argmax of V of pi star, V of pi. So you may say that, okay, why not to use dynamic programming? I say it's not possible to use dynamic programming, right? So here, like, do you know, the idea of here, when we started, we say that we can apply policy iteration to evaluate fu V of pi to convert V to pi star. That was the idea of policy iteration, and value iteration was quickly jump to V star, then get pi star. Like the idea was that I don't want to calculate all these V's. I do one of these two methods much faster, get this pi star. But now that I cannot do, so like there could be like some ideas here. Like some of you may say that, okay, you have a simulator, S, you get A, you get S prime. It's basically this simulator, it gives us one sample again from this. So do you think that if I had a policy, let's say a given policy, then if I follow that policy here, means that like if I am at state S1, then I follow policy of S1. I take that action, right? Then do you agree that the next state for me basically would be P of S prime given S and pi of S? Because the action is according to that policy. So in reality, I know that if I start from S, let's say that if I take A1, then there could be, if I could stop the simulator, it's usually not possible. Simulator is going. If I could stop simulator and I take A1 at different states, at the same states, I may get different S prime. It's possible. And the distribution of these would be the transition probability. So what is the challenge? The challenge comes from this. So if you think about it, so V pi, because that's V we need always. Because if we want to find the optimal policy, we have to find a policy that has the largest V. Let's come back to the initial things we had. Do you agree that according to Bellman equation, this is S pi of S, not action, R plus gamma V of pi of S prime. So I don't have this transition probability. That's the issue. And this reward at the same time, right? So what if I write this according to expectation? What would be the expectation here? R t plus 1 plus gamma V pi S t plus 1, given that your current state is S and you follow policy pi. Do you think is that correct? Look, this expectation, it says that you start from STS, then you follow policy pi. What are different next state? It gives you ST plus 1. ST plus 1 is here, S prime. But this expectation is with respect to this. Do you remember? This one was, we came in the past from this to this. So now even I wanna, this still doesn't give me anything. What if I write this one as expected value of RT plus 1 plus gamma RT plus 2 plus gamma 2 RT plus 3 in this way, given that I start from ST, S, and I follow policy pi always, means that here my AT would come from pi. Here all AT to infinity comes from this pi. So basically, if you think about it, this is R of ST, pi of ST, and ST plus 1. That is ST plus 1 is unknown. The other one is R of ST plus 1 is unknown, pi of ST plus 1, and ST plus 2. This is unknown, right? In this way you go. So we came reversely, right? We develop in the past Bellman from this to this. Because we don't have the model, we are coming back to this. So then this gives us, so V of pi of S is the expected value of this accumulated reward. We call this one GT, return. Given that you start from S and you follow policy pi. This GT is an accumulated reward, right? So let's say, for example, because I have not the simulator, if I could generate n trajectories, means that if I could generate this RT plus 1 plus gamma RT plus 2 plus in this way, n times, then each of them would give me G of I. So it would give me G T of I. Then I would approximate this by n. N is not number of states, it's by n trajectories. So this is Monte Carlo, meaning that, like, for example, let's take a look at here. Let's say I start from state 13 here. And let's say my policy pi is in this way. So this is my policy. Then so under this policy, if I start from state 13, I follow pi of 13. Pi of 13 says that come down. So let's say I have just simulator. I really don't know what is the next state. So you apply this, it's a stochastic system. Let's say it gives you 15. So you don't know what was the probability, just you see 15. And if it is 15, then you know the reward. Because like you have the state, action next state. So you know the reward. So the reward here becomes -1. Then you apply pi of 15. Let's say it becomes left, then the reward becomes 99. And you go to 60. So GT under this single trajectory, GT is a return, starting from state 13 and following this policy through simulation. It's -1 plus gamma 99, which is assuming gamma is 1 is 98. So it means that it's one possible trajectory return. But is there other possible trajectories? Yes, you could start from 13 if it is not deterministic. You take 13 down. Is there possibility to go to 14? Yes. Let's say simulator gives you 14 and you get -11. Then from 14, you have to follow policy. Policy of 14 is down. Let's say you go 99. So then you have to go, then you get 99. So your GT of second trajectory you generated from simulator is -11 plus gamma 99, which becomes 88. So Now, using just only these two trajectories, if you could afford more trajectories, you would generate. But let's say I could afford just two because of computation. So my V under this specific policy, if I would start from state 13, approximately is 1 over n summation of I is equal to 1 to n gt of I. Means that I got one time 98, one time I got 88, starting from the same state, following the same policy until the end. Then this becomes my approximate return. So this is now we want to solve this with Monte Carlo because we don't have the model, we have a simulator, right? So I want to apply policy iteration type of policy iteration. I can apply exactly policy iteration, but using Monte Carlo. So basically, I want to start with pi 0. I want to have Monte Carlo to evaluate the policy. Then I have V of pi 0. Because here I don't have the model, I cannot use Bellman equation. I cannot do approximate policy evaluation too. I don't have any transition probability. Then I have policy improvement. I get pi 1. Then Monte Carlo to evaluate. I get V of pi 1 and continuing this. So let's take a look at this, how it works. So I say how it works in example. So let's say that I have this unknown transition matrix and reward. When I say unknown, means that there is a simulator available, but I don't know exactly the numbers. So you can think in this way. Instead of that, there is a simulator that if you give S and you give A, it gives you S prime. So now for policy iteration that we had before, we would start with 1 pi 0. Let's say that my pi 0 is a random policy among all 4 possible policies here. It's A2, A1. So now my goal is that because I don't know the model, I have simulator, can I use Monte Carlo to evaluate the policy and get V of pi 0? Because if I could get, then I could apply value iteration, policy iteration, right? So it starts in this way. In episode, we call it episode 1. So you start with a random state. Random state, I have 2 states here, A or B. Let's say my random state comes A. Then I have to follow policy pi 0. What is pi 0 of A? Pi 0 of A, it says that take action A2. Because of this. It's a fixed policy, right? Then I go to simulator. In simulator, if I give here A, I get A2, I get one next state. Means that if I am at the state A, I switch, I go to B. Simulator gives me B. I don't know its probability. And what would be the reward here? Reward would be 4 because you take A2, but you go to B. So this is one tuple, they call it in RL. A state. Look, this is your state, SK. This is your action, AK. This is your next state, SK plus 1. This is your reward, RT plus 1. Or IK plus 1. So this is one tuple. So then it didn't finish. This is one transition. Then I went from A, after A2, I went to B. Then I start from B. This is exactly the same B. So from B, I have to follow pi 0 of B. What is pi 0 of B? It's A1. If you put it in simulator, B and A1, it stays B. And the reward becomes 5. So now I am at B. Pi 0 of B. Again, I have to follow. Look, this is exactly this. I'm just moving, right? So current state, take action. Action would be again A1. Is there a possibility to go to A? Simulator could give me 8 because it's a stochastic environment. Then the reward would be 0. Then here I have to start from, look, everything is here, it comes here. From A, pi 0 of A is A2. If I have it, I go to A, it's possible to stay A. There's a possibility. And get -1. Then I have A, pi 0 of A, it's A2. I go to B and I get 4, and in this way. I can continue until a long episode. So after continuing this, so this is one episode. You could have episode 2 too. So episode 2, you start with a random state. Let's say this time comes B. If it is B, you follow again the same policy. It's A1, you go to B and you get 5. Then you are in B, you get A1, then there's a possibility again you stay B, then you get 5. Then you are at B, pi 0 of B is A1. Then there is a possibility again go A, then A, pi 0 of A, A2, A, and R is equal to -1, and you go in this way. Let's say you go for a fixed episode, let's say 1,000, 100, something long, right? Not short. Then you generate multiple of these episodes with random initial states following policy pi, right? So any questions here?
Professor, a quick question.
Yeah, sure.
So this is stochastic, right?
It is a stochastic. We don't know its a stochasticity, but you assume that when I give here A to this simulator, the simulator has this transition matrix on the background. So for example, if you say that I am at A and I want to take A2. So it's basically you are at A, you want to take A2. So it could be either 90% you're going to go B, 10% you're going to go A. So you don't know exactly these probabilities, but you feed it in simulator. Simulator gives you the next state. That next state could be either B or A, but you don't know. You just see the result.
Oh, okay. But so I guess if we don't know what the probabilities are, then how do we feed it into the simulator?
Oh, simulator doesn't need a probability. Simulator is already on the back of these probabilities, right? I just put it just for we don't know these probabilities. Everything is inside the simulator. You give the current state, it's a black box to you. And the action, you just see the next state, right? Just the reason that I put here, just because I wanted just to understand that there could be an underlying process under this simulator that drives the next state.
I see. So for us, like, we just see the output, basically, of like what the next state is.
Exactly. Exactly. Yeah.
Okay,
So
got it. Thank you.
then, so now that I have this, I could generate, let's say, many of these episodes. So so I call these things episode under a fixed policy. Because like always, the policy is pi 0. I just episode, starting from random, I create this tuple. The tuples are trajectories, right? Then it's called, we have one first visit, Monte Carlo. This first visit Monte Carlo, it says that go and take a look at all the first visits of a state. So how many states I have? I have state A, state B. There are 2 states. What are the first visit of state A in these 2 episodes? So if you like let's say just first visit of state A. So the first visit is here. Look, A. So what about in the second? The first visit is here in the second episode. The first time that I observe A, I don't say that it's here because it means that it's starting from, like this is starting from this, following the policy pi and going to different states. So it means that like if you look at this reward, like in your GT, that is RT plus 1 plus gamma RT plus 2 plus gamma 2 RT plus 3. So if I start from state A and I follow policy pi 0, right? So the first reward I observe is 4 in episode 1. Then the second reward I observe is 5. The third reward I observe is 0. The next reward is -1. Then the next one is 4, and so on. So think in this way. It says that the return is starting from state sk A and following always policy pi. Look, always policy pi is summation of these rewards. You don't care about these next states because you start from this. You follow this policy, you got these rewards. These are your G. So they expect, so 1G T of 1, trajectory 1, so it got 4 plus gamma 5 plus gamma 2 0 plus gamma 3 -1 plus gamma 4 4. So what about in episode 2? Do I have a starting from a state A and following policy pi? Look, if you look at this, you start from A here, then you always follow policy pi. What are the rewards you get? -1, this. So GT of 2, again for the same. So it is -1 plus gamma, whatever you get here, plus gamma 2, whatever you get. This becomes G of 2. So the V under pi 0, look, this is all of them are pi 0. Starting from A is 1 over 2 of GT of 1 plus GT of 2. That's it. What about for state B? So what is the first visit of state B in the first episode? The first visit is B here. Means that if you start from B, you follow policy pi. What are the rewards you would get? The first is 5. It's not this. Because you start from B, you follow policy pi. This is the first reward, second, third, fourth. So for I think the correct way is right. Starting from B in episode 1 and following policy pi is 5 plus gamma 0 plus gamma 2 -1 plus gamma 3 4. If we had continued, we would continue, right? What about for the second? The first visit of B is here. Then always we follow policy pi. Look. So it's 5 GB of 2 is 5 plus gamma 5 plus gamma 2 1 plus gamma 3 0, no, -1. Then V at under policy pi 0 starting from B is 1 over 2 GB of 1 plus GB of 2. So look, if you generate multiple of these trajectories, for each trajectory, you count the first visit of all the states. Some states may not be visible here. Let's say it was always A. So it doesn't have first visit here. It has just first visit here. So the first visit of each state, you count the reward after that. Like for example, it's the first visit, the reward after that. Why? Because that's a definition of V. V says that starting from A, then following policy pi, what would be the accumulated reward? Here, starting from A, look, always I follow from here down policy pi, 0. What would be the accumulated reward? Then I would approximate V using these multiple episodes. It doesn't need to be 2, it could be 1,000. But that's a first visit Monte Carlo. So there is an easier way, like this is like an average. So we know that, like, for example, if we would have V of S under a policy, we could have V of S plus 1 over N. Let's say G at that state under trajectory N minus V of S. Look, this is exactly your Monte Carlo averaging. So it's like, for example, you have your return under the nth trajectory, you average with respect to previous one. This is exactly averaging. If you calculate this is basically this gs of 1 plus gs of 2 plus gs of n over n. That's it. It becomes your v of s. It's just recursively writing it. But there is a more popular way to write it, not as an average, as v of s is equal to v of s plus alpha. Instead of 1 over n, you could put alpha. G of s minus v of s. This is not average. If alpha is 1 over n, it would be average. But it just says that the latest trajectories have more value. For example, if something is changing in the environment and something is happening, we could use this v. So first visit Monte Carlo, this is the algorithm. So again, it's a first visit Monte Carlo policy evaluation. The policy is given to you. It's a fixed policy. We haven't improved it. Given a policy, you start with, so basically you start from one random state, then you follow policy pi afterward. So clearly, you start from S, you take A, you go to S prime, you get the reward in this way. Then it is episode 1, you follow again the same policy episode 2, the same policy episode 3, episode 4, right? So then you come back and say that, okay, this is my initial state, state S, this is another initial state, is here. Then you accumulate these rewards here, starting from these and down. These would give you, these rewards would give you GS of 1, GS of 2, GS of 3 to GS of 4. Then you could have V of pi of S as GS of 1 plus GS of 2 plus GS of 4 over 4. Is that correct? So this is the way that the policy evaluation works with Monte Carlo. Then next step, we're gonna talk about the improvement. So if I have pi 0, I could apply Monte Carlo algorithm with some trajectory to approximate V of pi 0. Then I wanna see how I can improve it. Right, that's a topic of next lecture. So any questions here? Okay, so thank you everyone. I'll post the lectures and I'll see you in person on Friday. Take care. Have a good day.